Welcome back. Let's continue this exercise. Last time we added prism layers to resolve the gap between the blade and the hub. Now let's focus on the interface mesh between the rotating region and the stationary region. For this interface, the geometry is a cylinder. One idea is to add prism layers on these interface surfaces. This interface is only used for data interpolation. So we are not applying boundary layers here. The goal is clean meshes on both sides, with good alignment and near orthogonal cells. To do that, go to Custom Controls. Right-click and create a new surface control. Rename this surface control. Open the part selection and select both interface surfaces, one on the rotating side and one on the stationary side. Click OK. Now in Controls, set Prism Layers to Custom. Here we can change the layer count and total thickness, and also enable Override Boundary Default. I want to change Override Boundary Default. If you click it, the tooltip explains the option. It lets you override prism layer settings on specific boundaries. For example, on inlet or outlet boundaries. Because by default you may not have prism layers there. Now go to Total Thickness. Switch it to Custom first. By default the layer count is 2, but here we only need 1 layer. Set Total Thickness to Relative and keep it around 50%. Great. Now the interface prism layer setup is done. Next, let's talk about the mesh far away from the propeller. Our inlet, outlet, and far field boundaries are far from the blade, so we can use much larger cells there. So I create another surface control. I name it Far Field. Under Parts, I select the far boundaries: far field, inlet, and outlet. Click OK. In Controls, I only change target surface size. I want a much coarser surface mesh in those areas. Open target surface size. It is relative to base, currently 10, which is about 9 millimeters. I don't need 9 millimeters out there. So I increase this value a lot. In this example, I set it to 1600, giving about 150 millimeters cell size. Compared to the 125 millimeters blade radius, this is reasonable for the far field, so we still have a few cells across that scale. Good. Now remember in Chapter 1, when we meshed the rotating cube case, we refined the transition between rotating and stationary regions. That refinement must keep the aspect ratio and transition quality acceptable. In that example, we created a slightly larger cylinder around the rotating region and used it as a refinement region. We will do the same thing here. Go to Parts, right-click, New Shape, and choose Cylinder. Create a cylinder that is a bit larger than the rotating cylinder. For the start point, move it slightly upstream in X. If you want, adjust the view so you can see the placement. Now set the end point downstream along X. For example, I set it into the negative X direction. So this cylinder is aligned along the X-axis. Now set the radius a bit larger than the propeller region. I set it to 18. Now you can clearly see which area this cylinder will refine. It covers the rotating region, plus some upstream and downstream distance. Click Create to generate it. You can also add it to the scene to visualize it. Click OK. Now you can clearly see the refinement cylinder. As we said, it is slightly larger than the rotating cylinder. This is the region where we apply refinement. Clear and visible. Now that the refinement cylinder is defined, go back to the mesh and open custom controls. Now we can create a volumetric control. Create the volumetric control. Under Parts, select the refinement cylinder. The only parameter I want to change is the trimmer size. I enable isotropic sizing. So the cells refine equally in X, Y, and Z. Then I set the custom size to 50. I am not making it extremely fine at this stage. With that, the meshing setup is basically complete. Now we can generate the mesh and inspect it. Right-click and click Execute to generate the mesh. It may take some time depending on your system. Once it's finished, we continue. Okay, the mesh is generated. Go to Scenes. Open the mesh scene with a double click. Now we should be able to see the mesh. By default, the representation is initial surface. Change it to latest surface/volume. Once you change it, the mesh appears. Now set the view direction. For example, use Y with Z plus up. This is the mesh we generated around the propeller. Now zoom in and inspect the quality. You can see our gap settings are applied correctly. The prism layers in the gap do not collide with each other. So we avoid zero volume cells and other bad cells. And we reduce high non-orthogonality issues. Now zoom in on the blade edges. You can see the edge refinement effect clearly. Overall, the blade mesh looks good, and it gets finer near the edges. Now look at the interface region. You can see the interface prism layer we added. It is clean and normal to the interface, so both sides align nicely. This makes interpolation across the interface more stable and accurate. Okay. Now, when we first created the mesh, we kept the inlet and outlet very close to the propeller. We did that only to generate an initial mesh quickly and keep the cell count low. Now we need to move inlet and outlet farther away from the propeller. A common method is extrusion. Extrude the inlet upstream and extrude the outlet downstream. This creates extra space in front of and behind the propeller. To do that, go to Operations and click New. Under Surface Preparation, find Surface Extruder and select it. When you create the operation, a new settings window opens. For part, select the static region. Now select the surface you want to extrude. First, select the inlet surface. It asks if you want to create a new part. Yes, create a new part. Set output to single-sided, so extrusion happens only in one direction. Set the extrusion distance to 1 meter. Enable Create Volume Extrusion as well. So we create a volume, not just an extruded surface. Also enable Execute Operation. Click OK. The operation executes. And it creates another operation called Volume Extruder. Open Volume Extruder and go to its controls. It asks how many layers you want along the extrusion direction. I set it to 10. For stretching function, change constant to one-sided geometric. Open the settings and choose the stretching model. Change it to thickness ratio. This means the cell size grows by a ratio as you march forward. By default, the ratio is 1. I change it to 2. Now that these parameters are set, right-click the operation and execute. You can see the volume is created, but it is not assigned to any region yet. So we cannot mesh it right now, and we pause here. We will come back later and generate the volume mesh. Now let's create the outlet extrusion as well. Go to Operations, New, Surface Preparation, and choose Surface Extruder again. Part is again the static region. And this time select the outlet surface. Select Outlet and click OK. Keep Create New Part enabled and keep the output as single-sided. Set the extrusion distance to 3 meters. Enable both Create Volume Extrusion and Execute. Click OK. Now Surface Extrude 2 is created. And it creates a downstream volume for us. If you select both volumes, you can see the upstream and downstream extensions. You can clearly see how the inlet and outlet were extruded. Now let's set the mesh parameters for the downstream volume. Select Volume Extruder 2, then go to Controls. Change number of layers to 40. For stretching function, change constant to one-sided geometric. Then set the model to thickness ratio. Set the ratio value to 2, meaning each layer size doubles as you go outward. So the mesh grows smoothly downstream. Now, each time we run these extrusions, STAR-CCM Plus creates parts under parts. You can see surface extrude and surface extrude too. These volume parts must be assigned to regions. Before we continue, let's rename them. I renamed the first one to Upstream Extrusion, and the second one to Downstream Extrusion. Okay, naming is done. Now select both parts. Click Assign Parts to Regions. You can see both parts are selected here. For each part, create a new region and create boundaries for all surfaces. Then click Apply and create the boundaries. Click Apply, then Close. Now under Regions, you should see 2 new regions: Downstream Extrusion and Upstream Extrusion. Now that the regions exist, we can run the volume mesh operations. Click Generate Volume Mesh. All pending volume meshes will run, and the full mesh will be created. Now the full mesh is created. Now we can create a mesh scene and inspect the overall mesh. The new annotation I added shows the extrusion meshes we created. It shows what the upstream extrusion and downstream extrusion meshes look like. Remember, we defined a number of layers for these extrusions. You can see those layers here and the aspect ratio and thickness ratio we set are applied gradually across the layers. The same idea is used for the downstream extrusion. The colored region you see in the middle is the original region. If we click Regions, we can verify static region, upstream extrusion, and downstream extrusion. One more important point: when we created the upstream and downstream regions, STAR-CCM Plus automatically detected a new boundary between them and the static region, and it automatically created an interface there. For example, here you can see an interface between static region and upstream extrusion. And another interface is created between downstream extrusion and the static region as well. Great. Now let's continue. At this stage, I can also add the drive part to this scene. I find the drive part and set it to include the entire region, so all meshed areas are visible. Now I go back to Mesh Scene 1. Since we updated the regions, you can now see what the full mesh looks like. If you look carefully, the extruded mesh is basically a copy of the original surface mesh, just extruded layer by layer. For example, the inlet surface mesh in the static region is extruded layer by layer upstream, forming the upstream mesh. And the same logic applies for the downstream extrusion. With that, this part of the exercise is finished. In the next part, we will set the boundary conditions and get ready to solve. See you in the next video.